Hi, my name is Rainer Jasper Anajon, matrix number 108172. In our kitchen, the refrigerator we use is a Toshiba model, and we have used this refrigerator for approximately 12 months now. Next, the fridge is placed 8.5 cm away from the wall in between two wooden cabinets. For the refrigerator we use, this model received a 4-star energy consumption rate, with the average energy consumption is 373 kilowatt per hour. Here inside the refrigerator we can see its spec plate. In the spec plate it shows that the refrigerant being used is R600A with the amount of 48 gram. Next, above it we can see the rated defrost power, which is 170 watt. The total storage volume of the refrigerator is 325 liter, with the fridge storage volume is 235 liter and the freezer compartment storage volume is 90 liter. We can see also other details about the refrigerator, like its insulation blowing agent, which is cyclopentane, and the rated voltage used is alternating current with a power of 220 to 240 volts, with the rated frequency of 50 Hz. Its climate classification is T, and the rated current in this refrigerator is 1.6 ampere. The height of the refrigerator is 166.6 cm. The length of the refrigerator is 67.8 cm. The width of the refrigerator is 59.2 cm. Moving on, the volume of water being used is 400 ml and the temperature of the water is 48.9 degrees Celsius. Right now, the second reading shows that the temperature of the water is 43.7 degrees Celsius. Right now it's 12 AM and I'm taking the third reading. The third reading shows that it is 35 degrees Celsius. Right now it's 12:30 and I'm taking the fourth reading. The thermometer shows that the temperature is 28.7 degrees Celsius. Right now it's currently 1 AM and I'm taking the fifth reading. And the water temperature is 24.2 degrees Celsius. 1:31 in the morning, and the sixth reading for the water is 21.8 degrees Celsius. It is 2 AM now, which means we have already hit our 3-hour marks. So our final reading of the water is 19.4 degrees Celsius. This is the completed version of the data logbook for the analysis. Here it shows that the temperature for the water is recorded for 3 hours for every 30 minutes. There are 7 temperature readings, and the time for the compressor at a work state is 2400 seconds, where the temperature at source is 27 degrees Celsius and the temperature at sink is 13.1 degrees Celsius. Next, this is the schematic diagram of the refrigerator. At the center, the refrigerator is denoted as R. The refrigerator absorbs heat QL from the low temperature reservoir, also called as the sink, at a temperature of TL. Next, to transfer this heat to a higher temperature, network input is supplied to the system, usually in the form of electrical energy, to the compressor inside the refrigerator. As a result, the refrigerator rejects heat to the high temperature reservoir or source at temperature TH. Moving on, this diagram shows the system boundary of the refrigerator. This diagram also shows the actual vapor compression refrigeration cycle with a clearly defined system boundary around the working fluid. The system consists of four main components, which is the evaporator, the compressor, the condenser, and the expansion valve. At the evaporator, the refrigerant absorbs heat QL from the refrigerated space, which is the sink. This causes the refrigerant to evaporate at low pressure and low temperature. Next, the refrigerant flows to the compressor, where it is compressed to a higher pressure and temperature. This process requires work input W net in from an external power source. From the compressor, the refrigerant moves to the condenser. Here, the high temperature refrigerants reject heat, which is QH, to the surroundings. The refrigerant condenses from vapor to liquid. From here, moving to the last component, which is the expansion valve. Here, the liquid refrigerant undergoes throttling, which reducing its pressure and temperature before entering the evaporator again. This process involves no work and ideally no heat transfer. This is the calculation of COP for the refrigerator. To find the COP, we are going to use the equation of QL over W in. To obtain QL, we use the equation of mCV delta T. Since the volume of the water is 400 ml, we assume its weight is 400 gram, which is equivalent to 0.4 kg. Referring to table A3 for water, we can get the CP or the CV of the water, which is 4.18 kJ per kilogram Kelvin. Then the T1 for the water is 48.9 degrees Celsius and the T2 is 19.4 degrees Celsius. With this information, we can calculate our QL, which is negative 49.324 kJ. Since the QL is in negative, the negative signs indicate that the heat is rejected to the surrounding temperature inside the refrigerator. Therefore, we can get our COPR for the refrigerator, which is 0.012. By the manufacturer's efficiency, we can get the COP, which is 0.39. This value shows that the COPR is lesser than the manufacturer efficiency COP, which is 0.39. This shows that over time, the COP of the refrigerator will decreases. Next, we can see that this is the equation to search for COPR reversible. The value of the COPR reversible is 20.58. For the value of COPR reversible and COPR, we can see that COPR is lesser than COPR reversible, which shows that this system is an irreversible refrigerator. This is the calculation for the entropy generation of the refrigerator. Since the refrigerator is a steady-state, steady flow process, we can assume that its change of entropy is 0. Then, from the equation, we can get the SGen of our refrigerator as 153.7 kJ per Kelvin. The largest source of energy loss occurs during the heat rejection at the condenser. This is because a very large amount of heat, QH, is rejected to the surrounding at relatively high temperature. The heat transfer across a finite temperature difference always generates entropy, and since QH is much larger than QL, its contribution to entropy generation dominates. Therefore, that is where the energy is mostly lost in the system. In conclusion, the COP actual of the refrigerator is 0.012, while the COP reversible is 20.98. This value shows that the refrigerator is an irreversible refrigerator since its COP reversible is larger than COP actual. The causes for the inefficiency is compressor inefficiencies and high ambient air temperature.